This is Algebra 2 with Trig, 3A.2a. We're talking about graphing rational functions. A rational function has the form of P of x over Q of x. We've recently gotten done with our polynomial unit. So we know that polynomials could be represented in function form with P of x equals. So theoretically, with these rational functions, we could have any expression on top and any expression on bottom. We're going to do specifically some simple rational functions, and that's when we have a constant number on top. So these are being considered simple ones because we have a constant number on top, but we will always have a variable on bottom. The inverse variation function, 1 over x, that's this guy here. It's the most simple one that you can have. We often consider it a parent function. This is considered a rational function because you have x in the denominator, or any expression in the denominator with a variable. So we're going to talk about the parent function, and we've said that that's 1 over x. It is a rational function that consists of two symmetrical halves known as branches. What I want us to focus on here is that this says symmetrical. We're going to use that to our advantage. Symmetrical. If we know where the points are for one side here, we can use that to help us know the values of the other branch. And any function in the form of y equals a of x is going to have the same format. And the same format's going to have the same domain and range. So the domain and range, what does this mean? We can all read it. It says the domain and range are all non-zero real numbers. But what does non-zero real numbers mean? It means, if you look here at the graph, this graph exists at every x value except 0. It never touches the y-axis. You cannot plug in 0 into this equation. And the range, you can get any y value, except you can never hit 0. There is no value for x that you can plug in to get yourself to hit 0. We can take 1 and we can divide it by a half. We can take 1, we can divide it by 1. We can take 1 and divide it by 10. Divide it by 100. You can divide it by whatever you want. And you're never going to get the value of 0, and you're not ever going to get a negative answer. So that's where we're having no real value. Okay? You can never have a range that includes 0 if you're working with this equation or any multiple of that equation. We create these things called asymptotes. An asymptote is the line where the graph cannot exist. If we can't plug x into this equation, we have what's called an asymptote at that line. It's a vertical asymptote. We also have a horizontal asymptote for the y value that we can never reach. And we talked about we can never reach 0. There's nothing we can divide into 1 that's going to give us a value of 0. You can never get 0. And I can't divide this by any positive number to get me below the x-axis. It's never going to become negative. So let's come on over here. Let's talk about graphing. We're going to graph, this would be considered y equals a of x. The a value is 4 over x. This is a rational function. We're going to graph it. We're looking for our vertical asymptote. What's the value of x that we cannot plug into this equation? If you take the number 4, we can divide that by a tenth. We can divide that by a half. We can divide that by 1. We can divide that by 4. You can divide that by any number you want. What can't we divide it by? You cannot divide it by 0. You'll get an error every time. Can't divide by 0. So that's called your vertical asymptote. Whatever makes the denominator, listen to that, whatever makes the denominator 0. 0 makes the denominator 0. That seems silly, but of course it is. Now you're going to pick numbers to the right. Listen to this carefully. We're going to pick numbers to the right that work with 4, because this problem has a 4 in it. We could easily just do 1, 2, and 3. That would be fine. That would work. But let's try not to be calculator dependent. So let's try to use smart numbers whenever possible. What numbers work with 4? What's a number that goes into 4 evenly? Let's just talk about the ones closest to 0. 1. 1 would be a great number. What happens when we say 4 divided by 1? We get 4. So what we're going to do is go 1 to the right when x is 1 and y is 4. 1, 2, 3, 4. We're right here. What's another number for x that works well with 4? 2 works well with 4. And if x was 4, how many times does that go in? Happens to be 2 also. That's a coincidence. So when it goes in there, x is 2, we're getting an answer of 2. Now what's another number that goes in? Okay, some people might say, well, the next number is 3, but 3 doesn't go into 4 evenly. I might need a decimal for that, and I don't know what that is without my calculator, so let's not worry about that. Let's find another number that works with 4, and that, of course, would be 4. 4 goes into 4. It goes into 4 one time. We don't need a calculator. Use smart numbers. Know what you're working with. So we're going to move to the right 4 times and up 1. So there is our branch. Now we could redo calculations on this side. If you want to recalculate the whole thing, you could easily plug in numbers. Some of you might prefer to do that. What I want you to get to understand is that these are symmetrical. You don't have to do all the calculations. So if this is our origin, and we moved 1 to the right and went up 4, what do you think might happen if we moved to the left 1? It would go down 4. If you want to test that, like what does that mean? If you plugged in -1 into your equation, you would see that 4 divided by -1 gives you -4. You don't need to fill out this side of the table. You can just use the symmetry to do that. We went 2 to the right. We went up 2. So now we're going to go 2 to the left. And where are we going to go? Down 2. And 4 to the right. We went up 1. So now we're going to go 4 to the left and down 1. And you can figure out their values pretty quickly without having to recalculate everything. You might say we're actually calculating it, but it's just such a simple example. You can make the table for that if you like. Where is the vertical asymptote? Vertical means up and down. So which value of x can this graph not exist at? What value of x can we not plug into the equation?
0.
We cannot plug in 0. That's why it was shaded out here. So when x equals 0, that's a vertical asymptote. So we're going to put a dashed line through our graph where x equals 0. And the horizontal asymptote, what y value? That represents your horizontal values. What y value does the graph never become? It never becomes 0. It does become 3. It becomes 3 at this spot right there. It becomes 4 there. It becomes 5 there approximately. 6 up there. It just keeps getting closer and closer to 0 but never touches it. It's a hard concept to understand. But our y value is 0. That's your horizontal asymptote. So if we talk about domain and range, domain is all the x values. So what are the x values that we can get? All the numbers, all real numbers, except 0. Or should we say x equals 0? All real numbers except x equals 0. And what's our range? What range value? We're kind of saying the same exact thing again. What are the range values we can get? We get values that are really down low. We get them up really close to the 0. We get them above the 0 and up forever. So you get all real numbers except y equals 0. And we didn't really have to fill out this side of the table at all. If you can make graphs without filling out a table, that's great. In middle school, we learned how to take numbers and plug them into an equation to plot points and connect. I'm trying to use Algebra 2 skills to have us plot points. And here we're using the idea of symmetry to understand where the new points are going without just using your calculator or just plugging numbers into your equation. But that always works. Your comparison, we're comparing it to the original parent function. The only difference here is the 4 on top. So it's a vertical stretch by factor of 4. That is the comparison between these two. This graph, 1 over x, was graphed right here. And 4 over x was graphed right there. You can see that instead of going up 1, it went up 4 times that amount. Okay, instead of going up a half, when x was 2, it went up 4 times that amount, which took it all the way up to 2. Okay, on the flip side, What do you see different about these equations compared to the one we just did? What's different about these equations? What does this have with it that the other equation did not have? Has an h and a k value. And we know what h and k's do. H and k does your translation. So we're going to take the same graph we had before. It's called a hyperbola when it curves to one side and curves to the other, called a hyperbola, and we're going to translate that graph. So there's two ways we could do it. We could graph the parent function and then translate every point. Okay? I'm going to suggest let's use the asymptotes and then use that location to plot points that come from our parent function. And that's going to combine the two into one graph. We're going to draw asymptotes. So we're going to have one asymptote at what value is it going to land at? It's going to land at the h value. When you move x minus 1, it's going to make the graph move 1 to the right. So we're going to have an asymptote at whatever the h value is. It's always the opposite. It's not negative 1. It's going to be positive 1. And we're going to have a vertical asymptote where? At k. It's going to be exactly k. It's not even the opposite of k because the formula is plus k. Then we're going to plot 3 points to the right. Now, I'm going to kind of explain it differently, I think. We're going to use a table to work with the parent function. And we're going to pick 3 points to the right of that original asymptote. And then we're going to plot those from the current asymptotes. And then we'll use symmetry to do the rest. But we're going to draw 2 branches. And we're going to be plotting the points x and y that approach these asymptotes. So let's go ahead and try to plot this graph out. So one thing we can focus on is what is the vertical asymptote of the original picture, original graph. This is the question we're trying to graph. So what's the vertical asymptote of that?
0.
If we're using the x minus 1 in the denominator, we want to know what makes the denominator 0. So we add 1 to get x equals 1. So we're going to have a vertical asymptote at x equals 1. Then we're going to have a horizontal asymptote where? At y equals 2. So we can make a dashed line at y equals 2. Label that on your graph. And we're going to use that as our new origin. That's going to be our new origin. We're going to pretend for a moment that that's our 0, 0. That took in account all the h's and all the k's for all the calculations we need to do. So now we're going to use the basic part, the part we haven't even talked about yet, this negative 3. We're going to do y equals negative 3x to make our table. So for this graph, what is the vertical asymptote? That would be 0. And what's a number to the right that works well with 3 or negative 3? 1 always works well. What's another number that works well with 3? Well, 3 can go into 3. And is there another number that, okay, if we had to, we could probably do that pretty easily? 6. 3 over 6 is easily a half, or in this case, negative a half. So what happens when we plug 1 in for x? We get negative 3. So we're going to come over here to our new origin. And where are we going to go? 1 to the right and down 3. So we go 1 to the right from this new origin and we go down 3. Now we're going to go 3. We're going to plug 3 into here. What happens when you take negative 3 divided by 3? You get negative 1. You should be able to do this without a calculator. So what are we going to do from the origin? Right 3, down 1. That's easy enough. And what happens when we plug 6 into that? 3 over 6. If you need to write it down, go ahead and write it down. That helps you visualize it better. That's going to become negative a half. So we have negative a half. So when we go to the right 6 times, 1, 2, 3, 4, 5, and actually I got to go a little bit more to get to 6, but I'm going to go down a half. And now that is my branch, and it approaches this asymptote. It comes up and would approach that asymptote. There you have it. How are we going to determine the other points? We could come in here and recalculate, but we can just count. We went 1 to the right and down 3. So from our new origin, we're going to go 1 to the left and up 3. There's our point. From our new origin, where are we going to go? One suggestion is to just think about it as switching the signs. 3 to the right and 1 down. We're now going to go 3 to the left and 1 up. It's symmetrical to what's ever happening on this one. 6 to the left. That's 1, 2, 3, 4, 5, 6, and a half up. And there we have the new points that make the branches. And we don't have to do so much calculations. We could do more calculations if you want. If you want to think about this as your asymptote, and you need to pick a value greater than your 1 asymptote, you're going to pick a value of 2. So you're going to take this value of 2 and plug it into the equation. Negative 3, 2 minus 1 plus 2. That becomes negative 3 over 1 plus 2. Negative 3 plus 2 is negative 1. So you have this point, 2 comma negative 1. It took you all those calculations to determine that. And you went 2 to the right and down 1. But we got that just by using simpler math and going 1 to the right and down 3. So that's what I'm trying to get you to realize, that you can do these major calculations looking at a much simpler graph and just use your asymptotes as your new origin. Use that as the translations have all taken place. You don't need to calculate every translation for every point that you do. Just use this new asymptote location to do it. What's our domain going to be? numbers. We get all real numbers except where x is 1. And what's our range values? All real numbers except where the asymptote is. So that is y equals 2. So here you could say we have a reflection over the x-axis. That's why the branch is on the bottom right and this one's on the top left, where in our other graph it was switched around. It was in the upper right-hand corner and the lower left-hand corner. Now we're in the lower right corner. It's because there was a reflection over the x-axis because of the negative. It has a vertical stretch by factor of what? What was our vertical stretch by? Looking at your equation. You're getting all this by looking at the equation. By 3. On this side, we said the vertical stretch of 4 was from having our equation with 4. This one has our equation with a 3. A negative makes the reflection. A 3 is our vertical stretch. Translated, right, how much? We went to the right. What was your h?
1.
And we went up how much?
2.
What was your k? That's the translated part. That's where the asymptotes went. It went 1 to the right, and it went up 2. So that's your transformations of what this graph is requiring of a really basic equation. Okay, our last problem that we have to work through. The time, t, is in seconds. It takes for sound to travel 1 kilometer is right here. This is the time it takes it to travel 1 kilometer, where capital T is the air temperature. So they're saying that the air temperature affects how fast sound can travel. How long does it take a sound to travel 5 kilometers when the air temperature is 35? So we're going to get time for 1 second is 1,000 divided by 0.6 times your temperature plus 331. This is going to give us how far it travels in 1 kilometer. 1,000 divided by, use parentheses, that's a requirement here, 0.6 times 35 plus 331. So we're getting 2.84 seconds. That's to travel 1 kilometer. We need to go how far? We need to go 5 kilometers. There it is. So what are we going to do to our time? Multiply that by 5 to figure out our time times 5. And that gave us 14.2 seconds to travel 5 kilometers.